Hello, my name is Minhao Fu. Today I would represent my research work named Wide Feature Projection with Fast and Memory Economic Attention for Efficient Image Super Resolution. Thank University of Electronic Science and Technology of China and Sichuan Artificial Intelligence Research Institute for their support. First, we introduce the wide feature, a view from the network WISE. The wide feature means that augmenting the number of processed features in convolution layers. While training a wider network have several advantages. For instance, a wider network could improve performance as well as depth and obtain a better generalization. Besides, training this neural network is friendly to GPU parallel training, but it still has some limitations such as overfitting problems and difficulty in reaching convergence. From the efficiency perspective, training a wider network could result in an explosion of computation complexity and memory consumption. Reparameterization strategy has been widely used in various computer vision tasks. It can reduce the number of parameters without compromising network performance. It has advantages such as better performance than the normal convolution and can get more benefit from overparameterization, and is applicable in associated and linear layers, but it still has some limitations. For instance, larger overparameterization not equal the better performance, and this complex structure has no essential effect to network depth, and the computation methods result in precision errors. Here is an overview of the associativity in reparameterization. The batch normalization layers, convolution, and their associations, which indicates that the different linear layers could be merged into one. This is our approach, wide feature projection, which is inspired by the residual connection. Wide feature projection could learn a wide feature in a further way by a cross-channel pooling in the side weight of the major bottleneck. This structure could largely alleviate difficulty in learning wide features and ultimately train a wider network. Well, about the best channel-wise pooling method, according to our extensive experiments, we found that a normal kernel size 1 convolution could better express this function. And this block could be applied reparameterization strategy because the linear layer could be merged and the invert bottleneck, as the figure shows, expand and a squeeze convolution could freely augment network-wise with this strategy. Ultimately, it can be merged in a standard convolution, and which has been proved that having the fastest speed in the mobile device. Another problem is that whether we need a strong regularization. Previous work which adopt a larger overparameterization use a strong regularization such as dropout or weight decay, but in super resolution task, some experiments show that this regularization would lead to a performance degradation, so we does not use it. This figure is our module architecture, named Wide Feature Projection, termed as WFPB, which consists of a standard convolution layers, and 2 wide feature projector. This is a formula about how to reparameterize WFPB, which is distilled from previous work, thanks to RIP-VGG and in SR task, RIP-SR and ECB-SR. In this section, we focus on the memory consumption analysis. We concentrate on the analysis of a kept memory, which is reserved for the future usage and is widely known in attention mechanism and research connection. Well, according to our observation in typical multi-branch structures, we get some conclusions. First is that kept memory is most affected by the multi-branch structure and the identity memory sharing mechanism. So, an effective method to reduce computation and memory is to avoid generate a large attention map. Here is the table of our comparison of peak memory consumption of different network structures. The first column is the identity connection, and the second is the attention mechanism, and the third is identity aid attention in the base block. We observe that with the branch number increase, the memory go on with a constant scalar. And for attention, we found that pixel attention, which generate a bigger attention map, costs the same size as the identity connection. And for the identity aid attention, we found that they keep the same memory as the attention mechanism. So there exists a memory sharing mechanism between the attention and the identity. Here is our figure to imply what is the sharing mechanism and the essence of memory consumption. So according to our conclusions, we propose a novel, fast, and memory economic attention, named FMEA, which costs little resource with much improved performance. From the fast perspective, the pixel-wise multiplication is factorized to a spatial-wise and channel-wise attention. And we avoid the pooling, concatenating, and splitting operation, which will cost much computation and memory. And as a minimalist bottleneck structure, it costs little resource to get improved performance. And from the memory perspective, such operation could largely reduce kept memory, and the attention map dimensional reduction support our memory analysis above. Here is our architecture of FMEA. Here is the ablation study of FMEA. We found that this factorization would not bring a performance degradation, but we could largely reduce the computation, the multi-aids, and the memories. You could say that the pixel attention cost about the 16.4, but our WFPN cost only 15.8. Finally, we would give our overall model architecture. For the backbone, we adopt a sequential network with a long skip connection, because the sequential network will largely reduce the memory consumption. And the components was composed of WFPB and FMEA They consist of residual, connection, and only attention. Here is our overview of network structure. This is the comparison with the state-of-the-art efficient SR models. We found that WFPN show more competitive effect and achieve better performance. Here is the table of efficiency comparison. This table shows that WFPN achieves the lowest memory and activations, the second lowest flops and parameters. The results indicate that our analysis about peak memory consumption have a good implication for real-world applications, and the reparameterization could largely reduce parameter. This is a visual comparison with other methods. WFPN yields more visually pleasant partners in the select test data. Finally, if you want to collaborate or connect with me, send an email or scan this QR code. Thank you for your listening.